Now we're going to come back and we're going to look at another example of parametric equations, a more widely used example of parametric equations. That is the study of projectile motion, which is usually a topic that's one of the first things you do in physics, okay? So we're going to look at how the parametric equations are going to be used in this context. So we're going to present to you this problem and look at some ways in which we can interpret this on the calculator and interpret this through parametric equations. Soccer ball is kicked at 65-degree angle with initial velocity of 12 meters per second, assuming that the force of gravity is 9.8 meters per second squared. And we can ignore the forces of air resistance, determine the following. Find the vertical and horizontal components of its velocity. All right, that's going to be the first thing we're going to do. We're going to cite this for you. Represent the path of the ball using parametric equations. I'll show you that. Plot the trajectory or the path of the object. Determine the horizontal distance traveled after 2 seconds. When does the ball reach its maximum height? What is the maximum height? When does the ball hit the ground? Determine the horizontal distance traveled by the ball when it hits the ground. So all these questions, all these series of questions can be answered once we get our sets of parametric equations. One note of caution, okay? Typically, these problems are going to be presented with the discussion in degrees. Okay, that is the launch angle is going to be in degrees. If the velocity is given in meters per second, then the force of gravity is 9.8 meters per second squared. If the velocity is given in feet per second, then the forces of gravity are in units of 32 feet per second squared. So bear that in mind. So let's look at how we proceed with this, okay? We get a sense that the path is going to be like this, okay? This is the trajectory. This is the path that the ball is taken, okay? And all projectile motion is parabolic in shape, okay? So are we going to find the equation of this parabola? Well, no, we're going to find the sets of parametric equations which would generate this parabola, okay? So, and of course, over here is where it starts, and here is after however many seconds where it hits the ground. This, of course, would be its maximum height. So let's put some things in there, okay? So assuming that the ball starts from ground level, we put in the axis in there, which is effectively the ground. And we want to know to what height it will rise, and so here we put in an axis to determine the height, okay? Since we want to know the location of the ball at a point in time in its trajectory, we will need to find sets of parametric equations. So that's what we're after here. What are the what is the function in chi for the x-coordinate of this path, and likewise, what is the function in y for the y-coordinate of this projectile, okay? And of course, these are parametric equations. Once we have them, okay, then we can key them in, our calculator will generate this path, okay? So let's take a look. Fortunately, okay, those are very generalized equations, very generalized equations right here, as we'll talk about, okay? Physics will teach us that projectile motion problems of this sort where the following information is provided. Initial velocity is v0, initial velocity. Launch angle, theta, usually in degrees. Initial height, well, h0, if you're throwing it from the ground level, then h0 is 0. Sorry about that, okay? Gravitational constant, g, again, as I said earlier, metric units is 9.8 meters per second squared, and English units are 32 feet per second squared. Here are the defining parametric equations for all projectile motion. All projectile motions. Here it is. Okay, it's very straightforward. They don't vary. Okay, what varies is what goes into them. The position at x, okay, is simply the initial velocity times the cosine of the angle times t. That's it. That's the position in x. Okay, moving horizontally in x, there's no gravitational constant in there. Okay, not to be worried about. Okay, the position in y takes into account, okay, the gravitational constant. Okay, so the gravitational constant, it keeps going back and forth, sorry. Gravitational constant is acting downward, so therefore the negative comes into play. It's negative 1/2 gt squared. Gt squared, g being a gravitational constant, 9.8 meters per second squared, or 32 feet per second squared. Again, v0, the initial velocity. Sine of the angle, typically measured in degrees, times time. The height, if at ground zero, height is 0. Okay, so what we were given was that this was launched at 65 degrees. Okay, for with an initial velocity of 12 meters per second. So we just plugged everything in right here. Okay. And right here, of course, is our gravitational constant cut in half. It's negative 4.9. We keyed those in for our x sub t and y of t, all right? And we're going to take a look at the graph, okay? So let's move from there, okay? Now, can we find some of these answers without the graph? I guess the graph is coming up next. There's the graph right there, okay? So, but we can find some of those values without even going to the graph. Okay, we go back. We remember we said there was a whole series of questions we wanted to answer here. So now we want to see how we can proceed to answer those. Okay, so let's take a look. All right. Determine the horizontal distance traveled by the ball in 2 seconds. Well, horizontal is driven by the x component, okay? And so there's the x component, okay? The only thing that you need to plug in is the time of t. So after 2 seconds, it has traveled 10.14 meters horizontally. When does the ball hit the ground? Well, the ball will hit the ground, obviously, okay, when the y value is 0. Okay, when the y component is 0, it's either not yet left the ground, or it is going to be hitting the ground. It's back on the ground. Okay, so we got our y component of the projectile motion as defined here, and that's quadratic, as you can see, and we're going to solve that for t. So that gives us 2 answers. Of course, we can clearly see that by pulling out the t initially. Gives us t equals 0. The other one is driven by the solution of this guy, which is 2.21. So that's the total time that it's in the air, 2.21 seconds. When does it reach its maximum height? Well, the maximum height is generally reached about if it leaves from ground zero, it ends at ground zero. Maximum height is going to be at half this time. Okay, I guess I go back and answer those questions later. Okay. Oh, here it is. The maximum height is reached about well, it is not at about. It is exactly at half this time. So if I go back and I evaluate the height, which is of course in y, at this time, it will tell me it reaches that height of 6 meters. Okay. Determine the horizontal distance traveled by the ball when it hits the ground. Well, again, it will be in the air for a total of 2.21 seconds. So if we go to the x position and evaluate that, then we see that it will travel a total distance of 11 and 11.25 meters approximately. So let's see what we have to do here. Okay. we may have to change our window settings here, okay? Because for one thing, we're having this ball in the air for a total of 2.21 seconds. Okay, so we can see that the T max is going to be, you know, somewhere between 2 and 3. So I want to adjust that appropriately. I'm adjusting that to 3. Okay, now the parameters in time. So how often do you want this being plotted? Well, okay, you know, if you leave the t-step at 1, then it's going to plot basically 2 points. So the t-step now is in time, so I want to see this in maybe every 10th of a second. So that's my t-step in every 10th of a second. Now you have to control the X and the Y window. And that's why we had to figure those things out first. We saw that it traveled, 11.25 meters horizontally and about 6 meters vertically. So I want to tweak out my window settings there so that I can see those things. Okay, and so having done that, I guess we're back to, that's it. I guess that's it for it. Okay, so so the thing to remember, okay, and you can work with these, and I will have plenty of these problems for you tomorrow. Okay, these are the generalized expressions. Okay, these are the generalized. Whenever we have projectile motion, okay, we have two equations. One representing its position in x, that's horizontally, which is independent of gravity. The other is in y, which is the vertical, which is very much dependent on gravity. Okay, and the components that go in there, the initial velocity, the cosine of the launch angle, the sine of the launch angle, h sub 0, the original height. At ground zero, it's going to be 0, and gravitational constant, which depends on whether you're using feet per second, in which case gravitational constant is 32 feet per second squared, or in metric at 9.8 feet per second squared. So sometimes you work with one equation, sometimes you'll work with the x equation, sometimes you'll work with y, sometimes you'll work with both. So typically the one thing that you're concerned about most is how long is it going to be in the air. How long is it going to be in the air is, okay, is going to be answered most directly by going to the equation in y and setting that equal to 0 and finding the time. You'll find c equals 0 at the launch time, and then you'll find the other time when it hits the ground again. So that will probably be one of the equations you'll be using mostly. Okay, so I'll have plenty of examples for you to work on, and we'll have fun with those problems in class.